Okay, so it's a great pleasure to welcome Nick Proudfoot from University of Oregon, who will be giving you can see it, Singular Hodge Theory for Matroids, Part 2. Take it away.
Yeah, thanks so much for inviting me. I'm going to make this almost entirely independent of Jacob's talk. So I won't assume that you were at it, or if you were at it, I won't assume that you retained much. So there's going to be some of the structures are going to reappear, and I'll say a few words when they do. But don't worry if you don't have his talk fresh in your mind. Okay, excuse me. Okay, so let me start by saying what a matroid is. There are famously a million equivalent definitions of matroids, so I'm going to do one that works for my purposes. So there's a finite set, which is the ground set, and there's a rank function. It takes a subset of the ground set and produces a non-negative integer. And it should satisfy the following properties. The only set with rank 0 should be the empty set. That's the loopless part, and that's just going to make all the constructions a little more convenient. In general, if you take a set and you add an element to it, you either keep the rank the same or you increase it by 1. And if I have a set S and two elements E and F, such that adding E doesn't change the rank and adding F also doesn't change the rank, then adding both E and F doesn't change the rank. So those are the axioms. And a flat is a set where adding any element does increase the rank. So it's a flat is a set that's maximal within its rank. So adding any element to it increases the rank. And the example you should keep in mind are realizable matroids. So suppose I have a vector space and I have a bunch of non-zero vectors. I said finite multiset because it's okay for some of the vectors in my list to be the same. Then the rank of a set is just the dimension of the span of those vectors. And you can see, only if it's the empty set will I have rank 0. Adding a single vector either increases the dimension of the span by 1 or it doesn't. And the third thing is satisfied as well. And a flat is just a set where if you take the span, you don't see any more of the vectors in it. So that's sort of the canonical example to have in mind. Okay, I need to describe an operation on matroids called contraction. So suppose I have a matroid M, so it's a set E with its rank function, and I have a flat. So I want to define the contraction on that flat. The ground set is just the complement of F. And I have a new rank function where the rank of a set is just the rank of S union that set minus F union that set minus the rank of F. And it's totally trivial to check that this satisfies the axioms, the 3 properties. What is the example you should have in mind in a realizable case, if I have E inside of V, finite set of non-zero vectors, and M is the matroid, what is the matroid corresponding, what is the contraction? It's the realizable matroid associated with the image of the points not in F inside of V mod the span of F, right? And the fact that F was a flat exactly guarantees that all of these things go to non-zero vectors in V mod the span of F. A few special cases to have in mind. If you contract the empty set, you have done nothing. If you contract the biggest flat, namely the entire set, then you get the unique matroid on no elements. Okay? So those are sort of 2 edge cases which are important. And in general, we're going to want to talk about the rank of a matroid. It's just the rank of the biggest set. And the rank of the contraction is the rank of M minus the rank of the flat. So that's immediate from this equation. Okay, so now I'm going to define, sorry, Ben, did you say something? No. I'm going to define the Kazhdan-Lusztig polynomials and some associated polynomials called Z polynomials. So this Kazhdan-Lusztig polynomial Pm of t and the Z polynomial Zm of t are uniquely determined by the following 3 properties. This is sort of an initial case. So if I have the rank 0 matroid, namely the matroid on the empty set, then the Kazhdan-Lusztig polynomial will be 1. If I'm not on the empty set, if I have positive rank, then the degree of the Kazhdan-Lusztig polynomial is strictly less than half of the rank. Note that fails when the rank is 0, right? Because half of the rank is 0, and the degree of the constant polynomial 1 is not strictly less than 0. but for anything of positive rank, this degree condition holds. And here's the interesting part. If I take all possible contractions and I add up their Kazhdan-Lusztig polynomials with a shift t to the rank f, then I get something that's palindromic. In other words, it's the same when I read it forward and backward. So if I take zm of t inverse times t to the rank m, that just means write the coefficients backward. I get the same polynomial. And in a minute, I'll do some examples that illustrate why these three properties uniquely determine the polynomials p and z. Before I do that, let me just say a few words about what's the relationship between these and classical Kazhdan-Lusztig polynomials. It's not a special case. It's also not a generalization. It's just an analogy. So if W is a finite Coxeter group with longest word W0, and these are the classical KL polynomials, whenever x is less than or equal to y in the Bruhat order. The analog of this palindromicity condition is we can still talk about a z polynomial, z of xz of t, and it's the sum over all y between x and z of a shift t to the length of y minus the length of x times the Kazhdan-Lusztig polynomial for the interval yz, and the Kazhdan-Lusztig polynomial not for the interval xy, but for the sort of opposite interval when you left multiply by w0. So if x is less than y, then w0y is less than w0x with a t inverse. And this thing should be palindromic. So let me answer sort of a couple of natural questions. One is, why is it that in the classical setting we have polynomials associated with intervals, but in the matroid setting I just had a polynomial associated with a single matroid? So in the poset of flats of a matroid, each interval is itself the poset of flats of a smaller matroid. And there are secretly polynomials associated with intervals, but the polynomial associated with an interval is just a polynomial associated with that smaller matroid. That's not true in the classical setting. If I take an interval in the Bruhat order, that's not itself a Bruhat order for some smaller Coxeter group. So in that sense, the matroid posets are a little bit simpler. For example, the interval from a flat f to the top flat is just the poset of flats for the contraction mf. That's the first question. The second question, over here, you see Kazhdan-Lusztig polynomials twice. You see the Kazhdan-Lusztig polynomial for yz, and you see the Kazhdan-Lusztig polynomial for w0y, w0x. Whereas in the definition, the matroid definition, I only saw one KL polynomial. So what's going on there? So given a ranked poset with some auxiliary data that I don't really want to go into, but it's the data of the R polynomials in the classical setting and characteristic polynomials in the matroid setting, there's a notion of right Kazhdan-Lusztig polynomials and left Kazhdan-Lusztig polynomials. In the classical setting, the Bruhat poset has an order reversing symmetry, x goes to w0x, and that implies that the left Kazhdan-Lusztig polynomials are the same as the right ones after applying this symmetry. In the matroid setting, the poset is not symmetric. That was really the subject of Jacob's talk last week, that the poset is top-heavy. There is no order reversing symmetry. So it's not true that the right and left Kazhdan-Lusztig polynomials are essentially the same. In fact, the left Kazhdan-Lusztig polynomials are all the constant polynomial 1. So really, when you see this is t to some power times a left KL polynomial times a right KL polynomial, but the left ones are boring. Whereas here you have t to some power times a left KL polynomial times a right KL polynomial, and the left and right ones are essentially the same family of polynomials. Okay, so that's all I'm going to say for now about the relationship to the classical setting. So now I want to do a couple of examples which just sort of shows why these three conditions really do determine the KL polynomials. But first, I need a simple lemma that says that the constant term is always 1. This is going to be great. This is going to tell me that if I have a KL polynomial associated with a matroid of rank 0, 1, or 2, it's automatically just the polynomial 1. Because remember, the degree is strictly less than half the rank. So as long as the rank is less than 3, the polynomial has to be just a constant. And I claim it's always going to be the polynomial 1. So how do you prove it? If I look at the constant term of the z polynomial, That's the sum of shifts of constant terms of Kazhdan-Lusztig polynomials of contractions. But the only non-zero term here is when the rank of f is 0. So I just get the Kazhdan-Lusztig polynomial of the contraction at the empty set evaluated at 0, which is the Kazhdan-Lusztig polynomial of m evaluated at 0. So showing that the constant term of Pm of t is 1, that's the same as showing that the constant term of Zm of t is 1. So that's what we need to show. But remember, this is palindromic, so that's the same as showing that the leading term is 1. Or the leading term, that it's monic, that the leading term is 1 times t to the rank of m. Okay, so recall this is the definition of the z polynomial. So when f equals e, we get a contribution of t to the rank of e, which is times the Kazhdan-Lusztig polynomial of the rank 0 matroid. So it's just t to the rank of m. So that's where we get our t to the rank of m term. So now I want to convince you that all the other terms of this sum don't contribute anything in top degree. Right, so when f is a flat strictly smaller than e, I have this term t to the rank f p mf of t. So the degree of this is rank f, and the degree of this is strictly smaller than the rank of the contraction over 2. The rank of the contraction is the difference between rank of f and rank of m. So that's rank of m plus the rank of f over 2, but since f is less than e, the rank of f is strictly smaller than the rank of m, so this is strictly smaller than the rank of m. So only the f equals e sum n contributes to the leading term, which proves that the leading term is 1. That's the end of the lemma. Okay, so now let's actually do an example. So my first example, I want a realizable matroid corresponding to 5 vectors in a 3-dimensional vector space in general position. So, you know, any set of 3 vectors out of my 5 is a basis. Okay, so let's think about all the flats and their contractions. So there's one flat of rank 0, and when I contract at that flat, I just get my original matroid. There are 5 flats of rank 1. If I contract one of those flats, I get a matroid of rank 2. So its Kazhdan-Lusztig polynomial has to be a constant, so it's just the polynomial 1. There are 5 choose 2 flats of rank 2, any 2 vectors. Those contractions are rank 1 matroids, so I just get the constant polynomial 1. There's one flat of rank 3, namely all the vectors. And there I get a rank 0 matroid, and its Kazhdan-Lusztig polynomial is again 1. So if I take Zm of t, I have the rank 0 flat that contributes Pm of t. I have the 5 rank 1 flats, they each contribute t. I have the 10 rank 2 flats, they each contribute t squared. And I have the 1 rank 3 flat that contributes t cubed. And now Pm of t can be at most linear. Its degree is strictly less than 3 over 2. And there's only one way to put in a linear polynomial here and make this thing palindromic. I have to get 1 plus 5t. Let me do one more example, so 1 dimension up. Let me take 6 vectors in general position in a 4-dimensional vector space. Well, again, I have 1 rank 0 flat, namely the empty flat. And when I contract, I just get my matroid back. I have 6 rank 1 flats. And if I contract at one of those, I get the matroid associated with 5 vectors in a 3-dimensional vector space. So the associated Kazhdan-Lusztig polynomial is 1 plus 5t. That's what we just computed. There are 6 choose 2, which is 15 flats of rank 2. And those things, the contraction now is a matroid of rank 2, so its Kazhdan-Lusztig polynomial is 1. There are 20 flats of rank 3. The contractions all have KL polynomial 1. There's 1 flat of rank 4, and its contraction has KL polynomial 1. So now I have the flat of rank 0, the 6 flats of rank 1, the 15 flats of rank 2, the 20 flats of rank 3, and the 1 flat of rank 4. This works out to Pm of t plus 6t plus 45t squared plus 20t cubed plus t to the 4th. And again, the degree is strictly less than 4 over 2. So the degree is strictly less than 2. So the degree is 1. It has to be linear. And there's only one linear polynomial I can add to this to make something palindromic. This 6 has to get bumped up to a 20. So the linear term has to be 14. And the constant term has to be 1. It's 1 plus 14t. So this is always going to work. Okay. Let me do one more example. I won't actually work through it, but I'm going to tell you the answer just to see what these things can look like. Let me take R20 and let me take the roots of SL20 and M the associated matroid. So there are 20 choose 2 elements in the ground set here. So this has rank 19. So the the span of all these vectors is 19 dimensional. So the matroid has rank 19. So the polynomial is going to have degree at most 9. And here it is. So just, I won't do this for you. You can check this as an exercise if you like. It's a polynomial of degree 9, and here are its coefficients. So they get pretty big. Let me comment a little bit on generalizing these 3 examples. The first 2 examples were what are called uniform matroids. Matroids realized by a collection of n vectors in general position in a d-dimensional vector space. So the first example we did was n equals 5 and d equals 3, and the second example was n equals 6 and d equals 4. So we can actually find a general formula here. So when d is n minus 1, this is due to myself and Max Wakefield and Ben Young. And then we generalized it for arbitrary d and n with Katie Gedian, my former student. And then a bunch of people came up with a different formula, again, for uniform matroids with d and n using different techniques. And then yet another formula, and then yet another formula. So we really have 4 independent formulas for the Kazhdan-Lusztig polynomial of uniform matroids, all using different techniques, and none of which is obviously the same as any of the others. It's kind of become a testing ground. Like if you think of some new interesting approach to computing KL polynomials, you try to compute KL polynomials of uniform matroids, and it's sort of hard but doable. That's kind of cool. How about generalizing the third example? What if I just take the roots of SLN for some arbitrary n? Well, I mean, I can compute any of them recursively. I mean, we've done this on a computer going even past n equals 100. I gave you the n equals 20 case, but we don't even have a guess for a formula. Now, what we do have is a guess for the leading coefficient when n is even. So the example I showed you was k equals 10, and the leading term is, the coefficient of the leading term is 2 to the k, 2k minus 3 double factorial times 2k minus 1 to the k minus 2. Again, this is just conjectural, by checking the first 100 cases. But we don't have a proof of that either. So, in my mind, these are sort of the 2 first infinite families of matroids that I think about: uniform matroids and braid matroids coming from the roots of SLN. And in one case, it's hard but doable. In the other case, it's at least now totally out of reach to compute a general formula. Okay, so now let me state the main theorem, which is that the coefficients of these things are non-negative, which is not at all obvious from the definition. So when M is realizable, this was proved in the paper where we introduced these polynomials with Ben and Max Wakefield. And for general M, it's proved in the same paper that Jacob was talking about last week with Tom Braden, Jun Ha, Jacob, myself, and Botong Wang. So the structures involved in the proof are the same structures that Jacob introduced last week. So let me remind you what they are. So first of all, for any subset of E, there's a minimal flat containing that subset. I said throw in every element I can without increasing the rank until I have no more room. And given a pair of flats, I can define the join, F join G, which is the closure of the union. It's the smallest flat containing the union. Jacob talked about this last week. And let me note that the rank of this join is less than or equal to the sum of the ranks of F and G. So that follows pretty easily from the axioms I wrote in the beginning. Okay. And now this is a definition Jacob made as well. I'm going to make it again. I'm going to define the graded Mobius algebra of M. It has a basis corresponding to flats. And the basis element y sub f is in degree rank of f. And the multiplication is given by the join if it works on degrees and 0 otherwise. So if I take yf times yg, it's y of the join of f and g if the ranks work out. And if the rank of the join is too small, then I just get 0. So that's called the graded Mobius algebra. And okay, we have a module over this algebra called IH of M. I'm not going to define that. Jacob talked a little bit about how to define it. He talked about this thing called the augmented showering, and it's the largest irreducible summand of that. I'm just going to take it as a black box for now. So I have this ring, which I just told you what it is, and then I have a graded module over this ring. I'll tell you after the break what it means in the geometric setting, in the realizable setting. But for now, I'm just going to say I've got this module. Okay. Inside my ring, I want to look at the augmentation ideal, the ideal consisting of everything of positive degree, although it has a basis given by the YFs, where F is not the empty flat. And I'm going to define this IH underline of M to be the IH of M modulo the augmentation ideal times IH of M. It's a quotient of IH of M. So here's a proposition that's not so hard. Last week, actually, Eugene asked about this sort of filtration of IH of M by powers of this augmentation ideal. And here I'm talking about the associated graded of that filtration. So I take the pth power mod the p plus first power. And it turns out this is just the direct sum of these IH underlines for all flats of rank p with a shift. This is true by definition when p is 0, right? This is saying IH of M mod M, IH of M. I take the unique rank 0 flat, that's the empty flat, and it's IH of M. So this is literally the definition of IH underline of M when p is 0, but it's true for higher p2. And that's not so hard. I don't mean that you should see the proof. I mean, I haven't told you enough about IH of M to do the proof, and it takes a little work. I just mean this is not the hard part of the paper. This is, relatively straightforward to prove. In contrast, the following two statements I'm about to make are extremely hard. So the first one, Jacob said last week, this vector space IH of M satisfies Poincare duality with respect to some pairing, and it satisfies hard Lefschetz with respect to some Lefschetz operator. I'm not going to go into the pairing or the Lefschetz operator. All I really care about is this symmetry on dimensions, right? If M is rank 5, then the one-dimensional part of IH of M has the same, degree 1 part has the same dimension as the degree 4 part. The degree 2 part has the same dimension as the degree 3 part, etc. This is really hard to prove, but it's true. The second statement is that this underline IH of M vanishes in degrees greater than or equal to half the rank. That's also really hard. In fact, both this statement and these statements are wrapped up in a huge induction where we prove Poincare duality and hard Lefschetz and Hodge Riemann, and this is part of that huge induction. So this is actually a very, very subtle and difficult statement. Okay, but now let me explain why these three propositions imply the non-negativity theorem. So I'm going to define a new polynomial p tilde, which is the Poincare polynomial of these underlined IHs, and z tilde, which is the Poincare polynomial of the non-underlined IHs. And I'm going to claim that p tilde is p and z tilde is z, which in particular implies that p and z have non-negative coefficients. Okay, so it's easy to see that p tilde is 1 when I have the rank 0 matroid. There's nothing there except one-dimensional in degree 0. When the rank is positive, this proposition exactly says that the degree of p tilde is strictly less than half the rank. And proposition 2 back here about the symmetry exactly says that the polynomial z tilde is palindromic. So I only need to show that z tilde is the sum of the shifts of p tilde for contractions. And then we get exactly the definition of the Kazhdan-Lusztig polynomial and the z polynomial. So how do I do that? So z tilde, that's the Poincare polynomial for IH. If I replace IH with its associated graded, I don't change with respect to the filtration, I don't change the Poincare polynomial. And by proposition 1, this thing is just the sum over all f's of IH of a contraction with a shift. And that shift has the effect of giving me a factor of t to the rank f. So it's just sum of overall f of t to the rank f times p tilde. So that finishes the proof, modulo those three propositions. So I thought this would be a good break point, and maybe after the break, I'll explain the geometric ideas behind the three propositions. So why would you expect those three propositions to hold for realizable matroids?
Okay, great. Let's reconvene in 5 minutes, around 2:32. Any questions for Nick?
So in these examples, is Z polynomial any easier? Like for SLN, for example. So you said
No.
that you don't know P polynomial, but Z polynomial, do you know it?
No, we've tried that too.
Yeah, it's pretty much the same thing as known. If you know the KL polynomial, you know the Z polynomial, but you don't know it in any cases where you don't, where you don't know the KL polynomial.
No, I was just thinking that there might be a slightly better formula because it's palindromic, you know, and
Yeah. I mean, we've looked at, I mean, we've computed that very far out. We've looked at generating functions for the Z polynomial and for the KL polynomial. You know, we can show that the generating function satisfies certain functional equations, but we can't solve those equations. Yeah, I mean, we just can't find anything nice.
But geometrically, like as you will explain, this equation of computing some explicit homology.
Yeah. I mean, moreover, so the matroids that I showed you, the uniform matroid on elements and the braid matroid, they both have some symmetry. So Sn acts, the symmetric group Sn, and you know, then the coefficients of these polynomials you can actually interpret not just as numbers but as Sn representations. So for uniform matroids, actually the nice answer to the question is to explain the coefficients of the KL polynomials of uniform matroids as Sn representations. You get nicer formulas. So that's also something we've tried for the braid matroid. You know, we try to understand the coefficients of the Z polynomial or the KL polynomial as Sn representations, and well, again, it's just very complicated. We don't see any patterns.
Is it some terrible plethism of plethisms?
Yeah, absolutely. Yeah.
Is the space easy to describe for braid matroid? Like homology of what space or intersection homology of what space you're trying to compute?
Yeah, I'll define the space in general in a minute, but I'll tell you what it is for braid matroids. So think about the configuration space of n distinct points on C, and I'm going to compactify it in a certain way. So first of all, I'm going to allow the distances to go to 0, so that I just get Cn back. Or I'm going to take modulo simultaneous translation, but I'm also going to allow the distances between the points to go to infinity. So I'm going to compactify inside of, you know, P1 to the n choose 2 by allowing those distances between points to go both to 0 and infinity. So that's the space.
I see. And you don't impose like any, you know, non-collinearity conditions or anything.
Not sure what you mean.
Okay, no. Whatever. So just compactify. I see.
Yeah, I mean you do have some conditions in the sense that, like, if the distance between these 2 points is finite and the distance between these 2 points is finite, then the distance between these 2 points also has to be finite, right? So there's some limitations on which coordinates can go to infinity and which you know, simultaneously.
But basically, you just take the configuration space, embed into P1 to the whatever n choose 2, and then you take the closure.
Exactly.
I see.
Yeah, and it's extremely singular near infinity. In fact, the KL polynomial is exactly sort of the measure. It's the intersection cohomology Poincare polynomial of the stock at the most singular point. I'll say that in a minute.
And the resolution, can you visualize that?
Yeah, I mean, by iterated blowups. I blow up the most singular point, then I blow up the strict transforms of the one-dimensional strata, then the two-dimensional strata, etc.
Is it related to M0n? So there was some model when you have endpoints and then you blow up all diagonals of equal dimension.
Yeah. So so if I look at the fiber, if I do the resolution and I look at the fiber of the resolution over the most singular point, I get, I think not M0n, but maybe M0n plus 1 or something. There's some weird shift. Yeah.
I see.
Should I start again? 11:32.
Yeah, sounds right.
All right. So let me now say some of the things I was telling Eugene in more detail. Okay, so let me tell you the geometry. So suppose I have this finite multiset of vectors. I have now a map from the dual of V to a product of A1s to an affine space where the eth coordinate is just given by pairing with the vector E, which is in V. Right, so this is a linear map. And so this is inside an affine space, A1 to the E, but now I take its closure inside of P1 to the E, the closure of the image of this map, and that's called the Schubert variety of E. That's exactly the space that Eugene and I were just talking about. And for any flat, let me look at the set of points. I mean, I can always talk about the eth coordinate of a point on my variety, and that coordinate can be any number or it could be infinity. And I want to look at the points whose eth coordinate, such that the eth coordinate is not infinity if and only if E is in F. So for example, if F is the empty set, that means that there are no coordinates that are not infinity, and I just get the most singular point, which is infinity in every coordinate. On the other hand, if F is the entire set, that means that no coordinates are infinity. So it means it's like I didn't take the closure at all. I just get phi of V dual. It turns out that U upper F is always an affine space of dimension equal to the rank of F. So you see that in these two cases. It's always true. And in fact, Y is the disjoint union of these guys. It's not immediately obvious that the set of indices at which a point is not infinity has to be a flat. But that's true. It's not so hard to show. So in fact, this variety Y has a nice affine paving. So it's, it has a paving by affine spaces indexed by flats, and the dimension of the affine space is the rank of the flat. Jacob talked about this a little last week. So that immediately implies that the cohomology and intersection cohomology vanish in odd degree. And if I look at the even degree part, my ring H of M really is just the cohomology ring of Y, but with degrees halved. And the module IH of M is just the intersection cohomology of Y. That explains proposition 2, which was that this thing exhibits hard Lefschetz and Poincare duality. I mean, that's just true of intersection cohomology of projective varieties in general. Okay, intersection cohomology is the cohomology of some sheaf, the IC sheaf, or some element of the derived category, complex of sheaves. And let ICYF be a stock of the IC sheaf at a point of the F stratum. So I have a natural map from the global intersection cohomology of Y to the intersection cohomology of the stock at the most singular point, at the empty set stratum. The stratum isn't empty. It's the stratum corresponding to the empty flat, which is the all infinities point. It's the most singular point. I have a natural map, and just by general work, generalizing an argument of Ginzburg, this map is surjective, and the kernel is exactly H2 of Y times IH of Y. So in other words, the stock vanishes in odd degree, and the stock cohomology vanishes in odd degree, and in degree 2i, it's just H2i of Y mod H2 of Y times H2i minus 2 of IH2i minus 2 of Y. So this is exactly this underline IH in degree I. So in other words, IH is the global intersection cohomology of Y, and underline IH is the stock of the IC sheaf at the most singular point, the cohomology of the stock of the IC sheaf at the most singular point. In general, when you have a variety of positive dimension, the cohomology of any stock of the IC sheaf vanishes in degrees greater than or equal to the dimension of the variety, and that gives you proposition 3, which was this, this degree vanishing for IH underline. It's kind of funny, when I was talking about those propositions, I was saying that proposition 1 was pretty easy. It's not that hard. That was about the associated gradient of some filtration. And 2 and 3 were really, really difficult. In the geometric setting, 2 and 3 are easy. I mean, they're not easy because they rely on like 100 years of algebraic geometry. But if you're willing to take algebraic geometry as a black box, they're easy, right? I mean, you know, proposition 2 is just Poincare duality for intersection cohomology of projective varieties, and proposition 3 is sort of part of the definition of the IC sheaf. The hard thing is proposition 1 about these associated gradients. So it's not that hard, but it's at least the hardest part. Okay, so remember I said that if M is realizable, then the contraction M sub F is also realizable, where you just take the image of the complement of F in quotient of V by the span of F. So that's another matroid, and let me take YF to be the Schubert variety associated with that collection of vectors. But it turns out there's a natural inclusion of YF into Y. You just take all the F coordinates and set them equal to infinity. And this is a well-defined map. And it's a normal slice to the F stratum. What I mean by it's a normal slice, I mean, the important property is that the stock of the IC sheaf of this smaller variety, YF, at its most singular point, is going to be the same as the stock of the IC sheaf at Y at this sort of intermediate point on the F stratum. So in particular, if I take the cohomology, stock cohomology for the IC sheaf of Y at this intermediate point, it's the same as the stock cohomology for the IC sheaf at YF at this most singular point. So that's the underline IH for the contracted matroid MF. Okay. Let me let JF be the inclusion of a stratum. So there's a spectral sequence where converging to the global intersection cohomology of Y, where the E1 page is made up by compactly supported cohomology of the pullback of the IC sheaf to the stratum. This is just a general way to compute. I mean, it would be true if I replaced the IC sheaf with any other sheaf. Just when you have a stratified space, you can compute the cohomology of a sheaf by taking pullbacks to strata and then running a spectral sequence. Because UF is an affine, well, sorry, this is just the compactly supported cohomology of UF tensored with the stock cohomology. And because UF is an affine space, its compactly supported cohomology is going to be one-dimensional in degree 2p and zero-dimensional everywhere else. So that we can just ignore that term and it gives us a little shift. And then now I sort of sum over all P and Q and I get the cohomology of IHY. So, I mean, because the spectral sequence converges, this thing has a filtration whose associated graded is the sum over all P and Q of this. Sorry, I should say that the spectral sequence degenerates because everything's concentrated in even degree. So there are no maps. So the E1 term is the same as the E infinity term. And then when I add up all the groups in the E1 term, I just get the stock cohomology for Y at a point on F with a shift. And as we just said, this is the intersection cohomology. This is underline IH of the contracted matroid MF with a shift. And that explains proposition 1. So that's where all 3 propositions come from. Let me quickly say something about the relation to the classical setting. It seems I didn't put in any pauses on this slide. Sorry. So suppose I have the Weyl group of a Lie group G, an algebraic group G. And for any element of W, I take the corresponding Schubert variety inside the flag variety. So this admits an affine paving, and the cells in the paving correspond to elements of the Weyl group below W, so in the interval between the trivial group and W. And the Kazhdan-Lusztig polynomial, the classical Kazhdan-Lusztig polynomial, is just the Poincare polynomial of the stock of the IC sheaf at a point in the cell indexed by X. And the Z polynomial, well, it turns out that when you take a KL polynomial where the second term is W0, the longest word, it's just automatically 1. So the Z polynomial is just t to the length of x times fxy of t, and it's just the global intersection cohomology of the Schubert variety. So in other words, the global intersection cohomology of the Schubert variety is the sum of shifts of KL polynomials. And the proof is exactly the same as in the matroid setting, because the Schubert variety has the affine paving. This is not quite the most general case, because I didn't tell you about ZXY. I only told you about ZEY, where I start with the identity element. When the first index is not E, it's a little more complicated. So I can take the opposite Schubert variety associated with X. In other words, the closure of the orbit of an opposite Borel, like lower triangular matroids instead of upper triangular matroids, and intersect the opposite Schubert variety with X with the Schubert variety for Y. So that's called a Richardson variety. So when X is E, the opposite Schubert variety is everything. So this is just Y sub Y, but more generally, it's something called a Richardson variety. This doesn't admit an affine paving. It does still have a stratification that we can use to compute intersection cohomology. And again, it's going to be true that this Z polynomial is the global intersection cohomology of the Richardson variety. That's a little less obvious. It doesn't follow from quite the same argument because we don't have the affine paving, but it's also true. I think I'm going to stop there.
Okay, thanks very much. Are there questions for Nick? Do I understand correctly that this opposite Schubert variety is like the normal slice?
Yeah, exactly.
I hear crickets chirping, so I'll just stop the recording and then thanks again, Nick.
Sure. Thank you.